Good evening, everyone. Welcome to today's problem solving sections, week 11. So, in today's class, we will see about the what is the difference between the flowchart and the FSM, and how to draw the FSM. So, we'll start with first summarizing the NPTEL lecture. So, in this class, we will see like what is the drawback of the FSM and what is the ASM and how to like build what are the building blocks of the ASM, and then modeling of the FSM using the ASM. So let's just start. So what are the drawback of the FSM? So if we have many inputs, say 32 bits in the input, then we will have 2 to the power 32 states. So drawing like this many states will become difficult, and for the FSM, complete FSM, we will be drawing all the states and all the transitions. So let's see many inputs and many outputs, and also we cannot typically, most of the inputs are don't care, and output also remain unchanged, so we go for the ASM. So here if you see, if we have a 32-bit counter, we need 2 to the power 32 states. And because of this, for the larger circuits, drawing the FSM is getting difficult. So we go for the ESM, and we will see some examples. So ASM is suitable for larger number of inputs and outputs. And let's see. So the goal is to represent using the RTL design. So we will have two parts: control part and the data part. So we will have a control path and the data approach or the data path. So if you see, this block represents the control path, and this is the FSM. This complete block represents the data path, and this is performing the data processing. So what is the ASM actually? It is the FSM plus the data path. Now this is the example of a serial addition, which we have already seen in the previous class. Like we have a full adder. So if you want to use only one full adder and perform say n bit addition of two numbers. So say this consists of this. So the shift register performs the shifting. So the first one output will be 0 0, and this shift is enabled, so enabling this clock also. So the first carry in initial will be the 0, because flip flop will be initially like reset to 0. Now sorry, full adder output and flip flop will be initially reset to the 0, like clear is on clear bit, so it will be the 0 value. So 0 1 and 1, so sum is 1, again carry is 0. So this result will be stored here, and this bit will be like removed, and the next shifted output will be 0 1, and this carry out, this 0 will come here. So again it is 0 plus 1 plus 0. So this in the next cycle will come here, and the shifting will happen. So this one will come here, and now it is 1 plus 1, 1 plus 1 plus 0. So it is 2. So 0 1. Now in the next cycle, this one has to come here, and the next bit, and this 0 will come here. So the next bit to add is 0 0, which will be 0 0, and the 1. So it is 1 0. So this one will come here. Again, we will obtain this result from here, which is 1 0 1. So in this way, we can perform like the n bit addition, and here we have like we are performing a plus b, and this is the gate which will be like getting the clock. So like we have a clock and the control signal. So whenever the clock is also high and the control signal is also 1, then this flip flop will be enabled. Okay. Next, ASM overview. So let's see the same serial addition. If we want to represent using the ASM, so first we will represent the control part or the control path. So we have to start initial state, and until this bit is 1, it is in the same state. So it's whenever g0 is equal to 0, it is remaining in the start state, and when g0 is equal to 1, it goes to the load as well as the clear state. So it will perform this run operation until this control becomes n. If the control is equal to n, it goes to the start state. Else it is repeating this operation by performing control plus plus. So the serial addition, this is the data path. We need a comparator which compares like whether the given number, the counter is equal to n, is greater than n or less than n. So if it is equal to n, then we have to say that we have like perform the n bit addition, and it will give the done bit. Go bit will come from the controller, and also the n bit values for A and B to the shift register. And we have this output going to the n bit output for the external world, and the feedback for the carry. So this is the data path. So if you see this, this is the that control. This will give the control signal when it is equal to n, and it will take the n input and the input where it is performing the control equal to 0 starting, and then performing the increment. So next, So till here we have not seen like what are the blocks we have for the we will use for the designing the ASM. So we will see that. Yes. So for ASM chart we have three elements. One is this state box. Whenever we have any state, like we want to represent any combinational value, say S so 0 is equal to 0, or a state we want to represent, say state S0 in a Moore machine. So we will use this state box. So if we have say three states, then like we will be using three, and each state box and its collected component will be executed in one cycle. That also we will see. And this is the condition expression. So if there is a condition, say x, when x is equal to 1, this branch will be executed. And when x is equal to 0, this branch will be executed. And this is the conditional output. So this is used for the in the media machine, and this is represented when the media machine output is equal to 1. So these are the three like elements of the ASM chart: state box, decision box, and the conditional output box. So with this we can design any ASM chart. So the state box, we can represent the name, say that state name as 0, and any code which is optional, and the operation inside the state box. So the operation will take place at the end of the clock period, and if we can represent like sum is loaded with 0, the carry is loaded with 0, or we are loading A, and say any combinational variable like s is equal to 0, or any operation s is equal to t plus v, and like this statements we cannot write inside the like which are language in a detailed language like statement we cannot write inside the state box. So if we are designing a more model or a more type output, so we can list the output signal inside the state box, and say example we can also like, for example we have a counter, so count is equal to count plus 1, like some the action which are needed to be taken, and say z is equal to 1, so we can just represent z. So what is decision box? So basic condition like logic flow control. So only the decision box depends on the input. So this is an input which is say x. Depending on this, if it is false, this statement will be executed. If it is true, this statement will be executed. And if it is some boolean value, so if it is equal to 1, this will be executed. Not equal to 1, this will be executed. Um, in the decision box we can also have vector decision box. That means if we have say 2-bit input, so we will have like 4 combination. We can also have 1 or if we don't want to represent like if it is a don't care condition, we can just represent. So it's like up to 2 to the power n outputs, or we can write like this x condition. If it is 0, if it is 1, again y 0 1. So here it will be 0 0 condition 0 1 1 0 1 1. So this can also be, and this is the conditional box which is usually used to represent the output of a Miller type machine. And usually if the output is 0, we use this conditional box to represent it to be. And these are the it is the undertaken condition on some earlier decision. So because whatever the decisions was like based on like output, this edge, so this computation is already done. So this output we can represent is in the conditional conditional box. Um, So both ASM algorithmic state machines can be used to model Mealy state FSM or Mealy finite state machine as well as the more finite state machine. They are able to model Mealy machines because of that conditional box, and they can also be model machines that are of the mixed type. So we will see some examples of the ASM by converting this FSM to the ASM chart. Uh, yes. I hope you were able to hear. I just presented with this ASM. What is the like why we want we are going to the ASM from FSM, because if we have like 32-bit counter, if you want to represent, we need 2 to the power 32 states. So with yes, and so for larger number of inputs and outputs, FSM is not like that suitable. And what is ASM? It is the consists of both control path and data path. So here this control path is generally the FSM part, and the data path represents the data processing. So ASM is the FSM plus the data path. So this is a serial addition which we have already seen in the previous class. So converting that into a control path, we start with when g is equal to 0. So when g is equal to 1, we load the value and perform this operation until the control value equal to n. So that control value, we if it is equal to n, we will like stop this operation, and until that we have to end with a and b values added to give the output, which goes to the output pin, and we have a comparator which performs whether it is equal to n, and this increments the control value. And so there are three elements in the commonly used in the ASM, which are the state box, decision box, and control output box. So, and this conditional box is conditional output. Conditional output box is commonly used to represent the Mealy machine output whenever the output is equal to 1. So because we have this conditional output box, we can also design the Mealy machine. And this is the condition box, like decision box, where we are taking a decision. If the x value is true, a set of uh, things needs to be like this path is taken, and if it is false, this set of things are executed. And if we have 2-bit input, then we'll have 4 combinations. This we saw. So before like going to the ASM examples, do you have any doubts? Yes. So going to the examples. So we have this is the like a more version because we have the output 0 for state A and output 1 for the state B. So we have two states. So we have two. Sorry, just so this here we can represent the output also directly. So this is called say z is equal to 0 is the output. So this is for the state box. We have a decision box whenever we have some conditional expression, and we have a conditional output box, say commonly used in the Mealy model. So example here say condition when the input D is equal to 0 or 1. If it is 0, it has to be in the same state A. So it goes to the state A. If it is 1, it is going to the next state, which is B. Now you are in the B state, so again we need a condition. If it is 0, again it goes to A state. If it is 1, it goes to, it remains the B state. So in this way, we are able to convert like this FSM into an ASM. So next, here again we have two state, and this is the for FSM for the JK flip flop. We have two input bits. So if J is equal to 0, whatever the value of K, Z is equal to 0. When J is equal to 0, this output is 0. This output is 1. So we are coming to the condition. When the J is 0, So whatever is the k, it will go to the A state. When j is 1, now in this B state, it will see if it is k is 1, or if k is 1, then whatever is the j, it will go to the A state. If k is equal to 0, that means it has to check for j condition. And whatever is the j, it will go to the B state itself. So in this way, the JK flip-flop FSM is converted to the ASM. Now, if we have a more FSM sequence of 2 ones, so this is a more model because output is represented inside a state. Now we have a initial sequence we are starting. So we have first one, we come here, another one. So after the two sequences of 1, 1, 1, the output will be 1 here in this state, and for the following next all the 1, it will remain in the same state. And if we get a 0, it will go to a state where the starting state. Also, one more thing, ASM has the timing information which FSM does not have, and FSM it is not possible to draw for bigger circuits like 10-bit counter. Okay, that I think we will see. Okay, so now tabulating this. Uh, so from A state, we are remaining in the A state if W is equal to 0, and if it is W equal to 0. If W equal to 1, we are going to the next state, which is B, and output is 0. So in this way, we have tabulated it. Next, the same more FSM is now converted to the ASM. So we have 3 states. So we need 3 state box, and we have a condition like if this W input is 0, it goes to the state A. If it is 1, it goes to a state B. And from the state B, again we have a condition to check if it is 1, it goes to state Z, and if it is 0, it goes back to state A. Okay. Again, now it is in this state, so it should either remain in the same state or go to state A. So if it is 0, it goes to state A. If it is 1, it remains in the same state. In this way, we convert this FSM to the ASM. Now for a Mealy machine, say again same consecutive 2 ones. So here we can represent output Z here itself in this edge itself. So we reduce by 1, we need only 2 states instead of 3 states. Say now the input is 1, the first one, and we have a next one here. So when consecutive 2 ones, output is 1. And further one, it will remain in the same state, else it will go to the state A. So now the ASM chart for the Mealy FSM. So we have 2 states here. So we need 2 state box. And again we check the condition. If W is equal to 0, it remains in the same state. If W is equal to 1, it goes to this state, that is state B. And again, if we have to check the condition. So in this condition, we have here the output 1. So we need to represent using this conditional um, output box. And This goes to the state B. So in this way, we can even represent the uh, Mealy FSM using the ASM chart, because we are having this conditional box, and this is represented only when the usually only when the output is 1. Next, if we have this modify counter, so we can use 5 here, like there are 5 states, so we can use 5 state box. And here in this Mealy machine, this is a Mealy machine, right? Because the output is at this edge. This is 0, this is 1. So if this condition 1, then we have to give the output 1 and it goes to this state again. So now if we want to represent a 10-bit counter, then it is not possible to draw or tabulate using the FSM, because of the problem called the issue arises is the state space explosion. So we have C is equal to 0. We perform the C++, incrementing the C, and it's a 10-bit counter. So 2 to the power 10 is 1024. So we should count from 0 to 1023. If it is reaching 1023, then this condition will be satisfied. It will be reset to 0. So we are able to represent using the two state box itself. So ASM chart, we can represent the 10-bit counter, which is not possible to be represented using the FSM chart. And also the ASM chart captures the timing information, which is not captured by the FSM. Yes, so with this, okay, so next, this Adobe is not okay. So before going on to some more examples, any doubts? JK, so for the JK flip-flop, um, it remains in the A state when it is 0 x, whatever is the value of k, it remains with when j is equal to 0. So when j is equal to 0, whatever the value of k, it is not checking the condition of k directly. It is like for all 0 or 1 value of k, it goes to state A. A is where result is equal to 0, and if it is 1, if it is 1, it is going to the state z is equal to sorry, yes, this is j, this is k. So again, whatever value of k, it is not checking. It is going to the state B, where z is equal to 1. Again in state z is equal to 1 in the state B. If we have k is equal to 1, k is equal to 1, whatever is the value of j, whatever is the value of j, it goes to the state A. And if it is 0, whatever is the value of J, it goes to state. Here also, if you want, we can represent one more conditional box K to say whatever value of K. Is it clear now? So we call this is the state. This is the state box. With one state box, whatever is the any conditional box like or the any conditional box or any of the decision blocks, whatever are connected to in one of the state box, that complete block is called as one ASM block. And this is another state box. So it is all the elements connected form the next ASM block. So we have two ASM blocks in this. So this output will be coming in the first clock cycle, means this will be in the next clock cycle. So every one complete, this is a state box and all this element will be executed in one clock cycle. So all the parts of the ASM block execute in one clock cycle. It includes a state and all its output going edges, conditional box, and conditional state boxes. So this is about ASM block. So this here we have only this is the state box. So every element connected to this also will come, this will also come. So till this completely it will be one ASM block. Say one. This will form the next ASM block. This will form the next ASM block. So there are now three ASM blocks, and this complete, say, one ASM block will be executed in one clock cycle. So if we observe here, this is a first like initial clock cycle. Clock cycle 2, it is an ideal state. Like this is an ideal state. Next in clock cycle 2, it goes to the MUL1, which is ASM block 3. So here it took like one clock cycle to execute one ASM block, and this is the next clock cycle. So here it will be based on the condition, and this it will go to the next ASM block if there is. So this is a serial addition. Let's see. So a melee FSM for serial adder. If the now if this is the FSM, we want to represent it using the ASM chart. Then we have two states here. So we need two state box. So this complete one will form one ASM block, and this complete one will form the next ASM block. Okay, so this is the state box. If x and y are equal to 1 1, it will go to the this state. If it is 0 0, then the output is 0. So there is no conditional box, but here we have the output to be 1. So for this we need to use this conditional output box. That's why we have separated. So we have an S state, then it goes to A. And here, coming to the state B, again x and y it compares. If it is 1 1, it goes to the state B with output 1. So we have a conditional output box. Whereas for 1 1 and 0 1, it goes to the state B. And xy, if it is 0 0, we need a conditional box because output is 1 and it goes to the state E. So here there are two ASM blocks. So this block will take 1 clock cycle and this will be executed in another 1 clock cycle. So to implement this, say like we need a next state logic and we have to uh, have like two states, Z0 and Z1. Let's just see this. So for this, we can use it to derive the expression for S and D. Uh, so that, yeah, we have the D and the S. When X is equal to 0 0, it goes to state this. Whenever it is 1 1, we have like we change the state. So to this, and if it is 1 0 or 0 1, it remains in the same state. So this is the like sum output. So 3 ones will give 1, 2 ones will be 0 1, the sum output. Whereas this one will be like 0 1 plus 1 will be 1, carry 1, carry 1, sum 1 and carry 1. So now using this q, x and y, we have to get the expression for S and D because D is the that feedback carry and S is the sum output. Okay, yes. Now we will go to the next example. N odd numbers. So we have three states. So we have drawn three state boxes. Whenever G is equal to 0, it remains in the same state. When G is equal to 1, it goes to state B. And again, it goes to the next state C without any inputs given here. If it is in the C state, when Z is 0, it remains in this state. When Z is 1, it goes to the state A. So now if you want to perform the sum of n odd numbers, we are now state ID. We start, if the go is 1, we will start proceeding with the C is equal to 1, S is equal to 0. The initial condition says S is equal to 0, C is equal to 1. And if the condition we have to count till the n is equal to P is equal to n. And it's odd numbers because from 1 plus 1 plus 2 is 3. 3 plus 2 is 5. So this will be the counting sequence from this. And P will be P minus 1. If it is going to 0, if it is this condition P is equal to 0, then it will be completed. Else it will be repeating this procedure. So again we have two ASM blocks here. So we have adders. Adders are like combinational circuits, so there is no control signal. Directly two inputs are given and one output. Now we have to we have a clear signal. Like when LSC is the load signal, when it is 1, then the value C is equal to 1, S is equal to 0 will be loaded. Say we are performing the clear operation. What does this clear will do is that it will make this C to 0 and S to 0. Now we have loaded this value, so it will start with initial value C is equal to 1 and S is equal to 0 till this P, which is loaded with N counter value. This will be decrementing till it goes to 0. 0 deduct will go to the output of this block data path, which will go to the control block, this 0 deduct. Till then, it will be performing the addition operation. So from 1, which will be incremented with 2, which is will give the next odd number. That next odd number will be keep on getting added until P is equal to N. So again, here we have the next state logic and the like the Z logic. So here, when we have to clear, when the G is 1, we are starting initially. T2 T0 is like the ideal state. So the first we load this value. Initially we clear the states like S is equal to 0, C is equal to 0, and we load the value. Once this is set to T1, it will be loading C is equal to 1, S is equal to 0. It will first add the first odd number 1. Then it will be incrementing the C by 2. So 3. And decrementing operation will be performed for P. If it is ideal, it will be T0 mode. And it will be done when all the, like when the 0 deduct is 1 and the T1 is like completed. What is the next state logic? Whenever it is not a 0 and it is T1, or it is in this two state. So this 0 deduct, yes, this is the complete connection, control path plus the data path. So this 0 deduct is the input to the control path. So it uses the next state logic and generates all these signals. Ideal and done will be the output pins. And if it is clear, it will be performing the clear operation. Now in this operation, we have a multiplexer here to load the value 1. Okay. So till here, any doubts? So if no doubts, I think I'll take some example of one. I will convert one Melia machine to ASM and one more machine to ASM. Before going to the further examples, so what are the components or the elements of the ASM? This is called the state box. When the condition is 1 or the condition is 0, so this is the decision box. And this is the conditional box, and it's used in the Mealy machine, so sometimes called as Mealy box also. And this is used only used if output is okay. So I will draw one Mealy state machine state diagram. S0 state, S2 state, S1 state. So Mealy, so it will be output will depend on the input. So here it consists of 3 states. So we need 3 state box. Let's start with the state S0 and initial input is X. Now the condition X, if the X is 0, it goes to the state S0. If X is 1, the output is 1. So we need a conditional box here. and it goes to the state S1. So from S1 state, so here the output is 1. So we kept the conditional box. Again, we have a decision x is 1 or x is 0. When x is 0, the output is 1. So this, and x is, again we have third state S2. This x is 1. We have to check for condition x is 1 or x is 0. If x is 0, output is 0. So same here. Again, we have a conditional blocks because output is 1, and it goes to the state S1. So this is the Melian state machine. Next, we will try converting one more state diagram to the ASM chart. So any doubts in this Melian machine conversion? Any doubts? Shall we move to the next example? More state machine. So now let's consider 2-bit input. So we will have 4 combinations. So we have 3 states, and this is a more machine, so we can represent the output of the state inside this state box. This is the state A, and we have 2 inputs x and y. Now we have condition for x, decision 1 or 0. If it is 0, again y's condition. This is one way of like design representing in the SM chart. So 0, 1, 1, 0. If it is 0, it goes to the state A. If it is, let me draw the next state also. If that is equal to 0, x 0, 1. Now this one, you are in the state, if it is 1 1, it goes to state C. And 1 0 or 0 1, it goes to state B. Same way, it goes to state C. If it is 0, it goes to state D. If it is 0 0, it goes to state C. 1 0 or 0 1, it goes to state A. And 1 1, it goes to state this 1 1. From state B, it should go to state A. And this 1 1 should go to state B. Any doubts? Yes, more machine. We have 3 states. So we have represented with A, B, and C 3 states. And when we have four combinations, because 2 inputs, X and Y. So X is equal to 0, 0. It goes to state A. Okay. If it is 0, 1, sorry, not this one. This one. It should go to B. So 0, 1 or 1, 0, it should go to B. And if it is 1, 1, it should go to C. So 1, 1, it should go to C. You are in the state B. Now we get 1, 0. It will be in the state B to this. So this one. Next, it is 0, 1. It goes to state, or 1, 0. It goes to state C. And 1, 1. It goes to state A. 1, 1 is this. And we are in the state C. 0, 0 will go to the state C, same state. And 1, 0 or 1, 1 should go to A. So this both combined goes to state A. And 1, 1 should go to state B. So this is going to state B. Is it clear now? So this is more machine. So inside the state, we have represented the output. So is equal to 0, 1. Now we will solve some more examples. So the English statement says that state A and input 0, then it goes to the next state A. If it is in the state A, if x is 1, it goes to the next state B. If it is in the B state, it depends on the input y and not on the input x. And depending on that, it changes the state. So there are two states, two input variables and two output variables. And so in the ASM, it is like FSM, it is to be complete. We say right all the combinations. So, but here Y combination we have not seen. Here X combination is not given. So FSM it is not like not complete. A state depends on X and B state depends on like Y. So in ASM all state need not be like defined. So then going to that chart, can we draw ourselves here? Let's just we have two states A and B, and output is 1 while it is in the state B, so Z is equal to 1. We have a condition, we have to make some decision whether it is 1 or 0. If A is 0, then it remains in the state A. We have one input X, I think meaningful. So, yeah, and if it is 1, it goes to state B. Now in state B, decision 1 and 0. If it is 1, it comes to the state B. If it is 0, it goes to the state A. So output is represented inside the state. So this is a more machine. Yes. So this is represented here. Output is represented inside. So it's more. Now in this example, we will see both the control path and data path. So the English explanation for the problem is like we have two registers R1 and R2 and they are storing say some value. So we have to load them. So it's like first we have to load R1, R2. Say R1 with value V1 and R2 with value V2. Then R3 is equivalent to R1 plus R2. So we also need a controller, say which takes this input start and which should give three outputs, and we will see this three output what are load 2, load 1, because we need to load the input and this. Yeah. So what are the inputs and outputs? Start is an input pin, clear, load 1, load 2. These are the output. And the result, like load 2 will load the result to just the data path. We are loading this first till here, like we will perform the clear operation. Then next loading, it will load this register. So we need LDR1. This is a combination circuit, so no other control signal. Once this output comes, this path will be executed if this LDR2, the load 2 is 1, so it will load this result. So the ASM representation, we are loading all the three register value to be 0 initially, and once it goes to the first condition, it goes to clear is, and then the load 1 after receiving the load 1 value, it loads the value 1 and 2. It performs this value. After receiving LD2, it will load to the R3. So this is the Q1, Q0, D1, D2. So in this we can obtain the D1, D2 equations, and by considering this as Q1 and Q0, we can obtain the three equations, output equations. So the first state, clear is 1. The next state, we have to load the values to the R1 and R2, and the computer combination result has to be loaded to R3 in the third state. Here the present first state is this 0, 1. Based on the 1 S value, goes to the next state. After going to the next state, it does not depend on the S value. It goes to the next state, LD2, and it comes back to the reset state. So these are the equations for the, now the we have this as some for the control block. FSM is now for the control path, and control path is giving these three outputs, which is going to the data path. Data path consists of an adder, which consists of load 1 from the control path. Now after loading this value, adder will perform the addition. Once this LD2 is 1, this value will be stored in this register, and initially this clear bit, if it is 1, it will clear all the 3 registers. Okay, before going to example 11, I think this example 10 is the complete example. So any doubts here, where we have seen the complete data path and the control path. Okay, so if no doubts, then going to the next example. So here the ASM chart is for the mod 14 counter. So 4-bit counter. If the value is less than 4 or 12, decimal 4 or 12, we have to perform certain operation. Like this A2 is equal to 1, A0, A1, A2, A3. A2 is equal to 1. This means it is 4, and this implies it is 12. If it is 4, is equal to 1, else is equal to 0. If both are 1, then only F is 1 and counter is reset. So the controller should give all the signals: E clear, E, set F, increment A. So let's see the data path. So we load the values. Now we will be incrementing the values. When E is equal, D is loaded with 0, E is loaded with 1. When the A2 is 1, and when A3 is 1, that is this one and this is also 1, F is loaded with 1. So this consists of 3 ASM blocks. So if we see this, based on this two value, this is filled. This is from the previous value. Now this is 0, 0, it comes here. 0, 0. Whenever this bit is 1, it should make E to be 1. When both are 1, 1, so from here and this are not right. When both are 1, 1, it goes to T2 state. In the next state only, it will be reflected for the F is equal to 1. For this, the control signals, so we can define the increment A value whenever the T1 is 1. Then we have to clear the A and F state, T0, the starting state. We are setting the F only when it is in the T2 state. When we are clearing the E state, when the A2 is 1, along we are in the T1 state, we will, and A2 is not 1. We will set when A2 is 1. So what are the procedure? Like what is the procedure to design the controller? We identify all the states and the suitable code. We need to define what are the state, input and output, and we have to obtain the state equation and then draw the circuit. Yeah, we'll start solving the questions. First question: how many ASM algorithmic state machine states will be there to model and implement a 10-bit counter? Uh, 1024 states for the FSM. For ASM, say the initial state C is equal to 0, S0 state. The next state, what is the operation? We have to perform the increment, and if we can compare this, the C value with 1023, now based on this we'll give the X value. If this X is 0, then we need to proceed with the state S1. If it is 1, that means we have performed the counting from like 10 to the power 10 is 1024. So 0 to 1023. Then we will go to the initial state. So we actually need two states. That's why we are going from the FSM to ASM. You can represent even a 10-bit counter easily using a X. Is it clear? Any doubts? Is it clear? Okay, next question. The important difference between a flowchart and an ASM is. Yes, we said that ASM consists of the clock timing, like one state and connected all its decision and conditional block will be executed in one clock cycle. But flowchart, ASM and flowchart are not same. ASM consists of timing information. So, clear? Next question. Which one of the following is not an element of the ASM chart? This triangle is called as state box. So state box is an element. This one with say input and its condition is called decision box. So this is also an element, and this one is called as the conditional box. So this is also an element. Data box is not an element. Next question. ASM is a powerful as modeling any more FSM or Mealy FSM. So ASM modeling is better as compared to any FSM model. Okay, next question. What is the true about ASM block? State along with all the associated decision boxes and conditional state box is an ASM block. All the parts of the ASM block executed in a one clock cycle. It is also true. All statements, decisions, and action execute in parallel in an ASM block. Yes, so all of the above. Next question. In ASM implementation, the only difference between a combinational circuit block and a sequential logic block of the data path or processing part of the digital system is that both combinational and sequential require the clock input. Combinational does not require clock. The sequential logic block require a clock pulse and works at the edge of the clock pulse. This is true. The combinational part controls the clock of the sequential part. False. So the correct answer, the sequential logic block requires a clock pulse and works at the edge of the clock pulse. Next question. The change of state in ASM chart is performed in, we have a control logic. Because control logic will generate the required signals and that will be processed. So ASM chart it will change the based on the control logic. Next question. The box that tells the effect of the input on the control subsystem is called. This is that box, right? Which tells based on the condition 1 or 0. This is called a decision box. Okay, so any doubts still here? Fourteenth example. This one, mod 14 counter. Yes. So the mod 14 counter, like we have 4-bit counter, and here we are saying that based on this E and F, like we will be performing certain operations. So E is 1 when A2 is 1. That means it is either 4 or 12. And both are 1, that time only F is 1. So the counter is reset. So the controller should generate the required control signals for clearing the E, setting the E register, F, clearing the F and A register. A is that 4-bit value, so A value. And this will go to the data path where we have 3 registers. 2 1-bit register EF and 4-bit register for A. Now ASM chart, we are in the initial state. So if it is 0, we will remain in T0. If it is 1, we will load the values 0, 0, like clear the value. Next, we will increment A with A plus 1. Now, we will check the value for A2. If A2 is 1, then E should be set to 1. Otherwise, E is 0. Now, when A2 is 1, we should check for A3. If A3 is 0, then we will be in the same state. If A3 is 0, if A3 is 1, then we will increment, set the value of F to 1. And timing wise, we have 3 states. So all the 3 states will form the different ASM blocks. So we have 3 ASM blocks. And this one, we just represent the timing where value, like where E and F value. This control value, CTR value, counter value will come to the E and F after 1 clock cycle only. And condition will be checking from this directly, CTR value. And here 1 1 first it occurs. So here it should go to state T2, T2. Then it is reflected in this E and F. And then from here it is going, after 1 clock cycle, it should go to the initial state. Yeah. So, is it clear? Any other doubts? Any doubts? E and F value in the timing chart. Yeah. This one has come from the previous value. So we will start from here. This will be A3, A2, A1, A0. So E is equal to 1, then A2 is equal to 1, and F is equal to 1, and A3 is equal to A2, both are. So this is 0, 0. From here again 0. This is also 0. Here we have the first one. So this comes to E. And here, till here, we have E is equal to 1. Again, this, it is E and F are different. Like A3, A2, A2 is not 1. And for F to be 1, A3 and A2 both should be 1. So both are it's 0, 0. Coming to this state, the E is 1. First we are checking for the E. Then only it is going to the next state where F is taken. So it goes to the state 1 0 and state is T0. In the next state only F is going to be changed to 1 1, and when it is going to 1 1, it should go to the this initial state. So it should go to T0 state. Is it clear? Any other doubts? Tomorrow again we will meet at 6 to 8. We will have one summary section. Like I will summarize some like all the concepts in each class, and we will solve some questions from each topic. Like in the starting classes, we have seen some switching algebra, some theorems like De Morgan's theorem, consensus theorem, and we will see just one example for SOP, POS. Number system means like we will just take some 2 3 examples for conversion, and next like gray code, binary code means how to convert it, and Verilog some codes for Verilog, and again like we will just summarize tomorrow 6 to 8. I think we will summarize from the starting classes, and this week 11 and 12, like till week 10 we can summarize, and some questions we will. So any other doubts? ASM block. Okay, so if we take this example, okay, in this what will be the ASM block? If we see, this is one state box, so all the till this connection is not included in this. So till this completely is in ASM block 1. From here we have a one state box, and all the its connected conditional box and the decisional box will come to the next. So this will be another ASM, and this is the state box 3 with this complete. This will form the ASM block 3. So this block, you see, this is like going to one flip flop and then checking the condition. So this is like combination. This is also some combination giving the output, but this is the sequential element. So the complete ASM blocks will be like executed parallelly with within one clock cycle. So this will be executed in the another clock cycle. Is it clear? Any other doubts? So if you have any doubts, you can ask. I'll just save this files. Yeah. Any further doubts? So in ASM, we will be using the April 12 completed course after conducting live classes. I am not sure. Like we have week 12, one more live section on April 15th, Tuesday, and Wednesday, April 9th, summary section. So these are two uh, classes for me. On April 15th, we will cover the week 12 lecture, and on April 9th, we will cover the summary session, say from the first week to the 10th week, and maybe some questions from week 11. So this high level means like at the RTL level usually, and it's like we'll try to use like simplest architecture possible. So like we have identified the number of states and we have used a state box for each of the state, and we wanted to know like we consider what are the inputs, outputs, and the states, and then we derive the equations, and we have a control path separately, data path, and we connect them. Yeah, this is a procedure for ASM chart. If no doubts, then we can end today's session. Yes. Okay, so if no doubts, then we can end today's session. Thank you so much for joining. Uh, yeah, I will wait for 2 minutes. Tomorrow live class link, it is same link, the same link which you have joined today. Okay. Yeah. Thank you so much for joining. I will.